A system of equations may have no solution. By no solution, I mean that when trying to solve for the values of the unknown variables, there is no set of values that satisfy all of the given equations. Consequently, we are unable to get left-hand side equals right-hand side. When a system of equations has no solution, the system can also be called inconsistent. We can write a system of equations as an augmented matrix and solve by row reduction. As soon as we see all zeros for coefficients and a non-zero constant, we know that the system has no solution. In fact, it is not necessary to row reduce to row echelon form or to reduce row echelon form. Here are some examples of augmented matrices that show the system has no solution. Let's say we have a system of three unknowns, x1, x2, and x3. We row reduce and eventually get this result. In the third row, we have a bunch of zeros for coefficients, but then a non-zero answer or non-zero constant. If we were to interpret the third row as an equation, we would get 0x1 plus 0x2 plus 0x3 equals 1, or 0 equals 1. But 0 is not equal to 1. This contradiction means that the system has no solution. The system is inconsistent. In another system of equations, we have the unknowns w, x, y, and z. And after some row operations, we get this result. We have this row, which has zeros for coefficients, but then a non-zero constant. This system is also inconsistent. If another system has the 5 variables, apple, soccer ball, diamond, sun, and moon, and with some row operations, we get the second row. Coefficients are all zeros, but then a non-zero constant, 5. Or in the fourth row, we also notice the pattern, all zeros for coefficients, but then a non-zero constant, -2. We know that this system of equations has no solution and is inconsistent. We're asked to solve the system of 2 equations and 2 unknowns. The unknowns are x1 and x2. We transfer the information from the system of equations into an augmented matrix. The first column will be x1 and the second column will be x2. The third column will be the answers, or some people call them constants. The first equation has 3x1, -5x2, and the answer, or constant, is 8. The second equation has -6x1, 10x2, and is equal to -6. Now we row reduce, trying to get as many zeros as we can in this augmented matrix. Looking at the 3 and the -6, we have a common factor of 6. We can cancel that -6 by adding 2 times 3 to the -6. Row 2 plus 2 times row 1. -6 plus 2 times 3 is 0. 10 plus 2 times -5 is also 0. -6 plus 2 times 8 is 10. And right away we notice this pattern of 0 for coefficients, but non-zero for the constant. If we were to interpret the second row of this augmented matrix as an equation, it would read 0 times x1 plus 0 times x2 equals 10. In other words, 0 equals 10. This is nonsensical. 0 does not equal to 10. Therefore, this system of equations has no solution. We can also call this system inconsistent. Let's do another example. This system has 4 equations and 3 unknowns, x, y, and z. Weird people say z. We put the information from the system of equations into an augmented matrix. The first column is x, second column y, and third column z. Equation 1 has -1x, 2y, 1z, and is equal to -2. Equation 2 has 3x, 1y, -2z, and is equal to 5. Equation 3 has 2x, -3y, 2z, and is equal to 0. Equation 4 has 1x, -2y, 3z, and is equal to -1. We row reduce this matrix, trying to get as many zeros as we can. The first thing I notice is that we have a 1 and a -1. We can cancel that 1 by adding that -1 to the 1. Row 4 plus row 1. 1 plus -1 is 0. -2 plus 2 is 0. 3 plus 1 is 4. -1 plus -2 is -3. Then, looking at the 3 and the -1, if we go 3 times -1 added to that 3, we can get rid of the 3. Row 2 plus 3 times row 1. 3 plus 3 times -1 is 0. 1 plus 3 times 2 is 7. -2 plus 3 times 1 is 1. 5 plus 3 times -2 is -1. And then we can clear that too by adding 2 times -1 to the 2. Row 3 plus 2 times row 1. 2 plus 2 times -1 is 0. -3 plus 2 times 2 is 1. 2 plus 2 times 1 is 4. And 0 plus 2 times -2 is -4. We're now done with the first column. There's nothing else we can use to clear that -1 because everything else other than that -1 in the column is zeros. We can try to get zeros in other columns. I see a 4 and a 4. We can easily get rid of one of those 4s by subtracting. We can go row 3 minus row 4. 1 minus 0 is 1. 4 minus 4 is 0. And -4 minus -3 is -1. Looking at the 7 and the 1 in the second row, we can cancel the 7 by subtracting 7 times 1. Row 2 minus 7 row 3. 7 minus 7 times 1 is 0. 1 minus 7 times 0 is 1. -1 minus 7 times -1 is 6. Next, we can cancel that 4 using the 1. If we go row 4 minus 4 times row 2, we can cancel that 4. 4 minus 4 times 1 is 0. -3 minus 4 times 6 is -27. And now we see a row of zeros for coefficients, but a non-zero constant. In the fourth row, if we were to rewrite this fourth row in terms of the variables x, y, and z, we would have 0 times x plus 0 times y plus 0 times z equals -27. Simplifying, we have 0 equals -27. 0 is not -27. This is a contradiction. Therefore, the system of equations has no solution. We can also call the system inconsistent. I just want to emphasize that the steps that we took to simplify this augmented matrix in this example is just one out of many strategies of solving augmented matrices. Personally, I look for common multiples between rows and then add or subtract these rows to get zeros. And you may have another way of solving that works just as well. Do what works most accurately and fastest for you. Another comment I want to make is that we actually don't need to solve the system fully to get into row echelon form or reduced row echelon form. In the case of an inconsistent system, as soon as we see a bunch of zeros for coefficients and then a non-zero constant, we can automatically say that the system has no solution.